Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and it's great to have you with us here today. Hi to people in chat, hello to people who are here at the moment. I've seen Kai in chat, I've seen Alfie in chat already, and some anonymous people as well. Hi to people who are just joining us, and hi to Prisma, who's moderating chat for us. Prisma's a current student. Hi to Casey as well, I think. There's Casey. Hi to people. Hi to Harriet as well. I'm guessing that I've got things set up correctly because people haven't told me it's wrong yet. Great to be here. We're doing something slightly mad in that it's currently the open days. We've just done 2 open days at the University of Oxford, doing a selection of maths talks, and people have been visiting colleges. It's been a really busy 2 days. At 5 p.m. on the second day, I'm exhausted, but we're going to do the maths club anyway. We're going to do some maths content. Hi to Ali as well, good to have you with us. So just to give you an idea of the open day first, if you weren't here at the open days and you want to get an idea of what it was like, we recorded and live streamed 3 of the talks on the main channel. On the main channel. So if you want to try and find that video, here's a video of that. Pay no attention to my recommended videos. So here's Vicky Neal. Vicky's just written Fermat's last theorem on the board. X to the n plus y to the n equals z to the n. Very impressive stuff. Thank you, Vicky. So Vicky did a talk about pure mathematics. We had a talk by Ian talking about applied mathematics. There's Oxford spelled out of Nesquik letters and other applications of mathematics like these elephants and ants on swings and things. Ian's talk has lots of interesting props that he brought along and demonstrated. Let's see if we can find the table of props in here somewhere. Oh my goodness me. So table of props and things going on in the applied talks as well. Casey was here and is now in chat underneath as well, so that's fantastic. Always good to have people coming along as well. Kai's listening to this in the car. Alfie's going to come back for the September open day. September open day is going to have similar content, I think. Let's see if I can. Nope, that's gone over there again. There we go. Close that. There we go. So if you want to catch that, that was over on our main Oxford Mathematics channel. So if you want to catch that on the, we got to broadcast on the main channel for a change. So if you subscribe to that one, you can find it in their uploads as a 1.5 hour video covering maths at Oxford, pure maths and applied maths. Hi to CRM as well. Yeah, there is me in there as well. There's half an hour of me. If you're aware of Maths Club, then you're sort of probably also aware of where to find things on our website, such as advice about applying. But if you want to see a half-hour video about that, of me, I didn't realise, I watched the video back, the lighting in there is quite theatrical. We had the lighting set quite low, so it's sort of quite gloomy almost on my talk. It's a little bit spooky almost. It was really good fun. Good. Prisma's trying to moderate, and somebody has put some malicious code, malicious code in there as well. So that's going on too. Hang on while I reject this call. No, that's not happening. There we go. Malicious code is not going to happen. There we go. Cool. Good. So link in chat if somebody helps out. That might be good. Might be for the best. Okay. Coming up today, my plan is to repurpose talks that we've got. That is not going to happen. We're going to repurpose things that people have come up to. People have come up to me to show me bits of mathematics at various events recently. My sort of slightly cheeky plan was to take all of the maths that people have shown me and to repurpose it into a math live stream on Oxford Online Maths Club. So something I'm going to try and do is I'm going to try and cover different bits of mathematics that people have shown me. Sort of like a show and tell session, to have different things that people have shown me repurposed into a maths club, putting it all together. It's based on something that someone put really clearly when they came up to me. They said they were the only person in their school who is interested in maths at Oxford. The only person who's interested in maths in their school. They didn't really have anyone to bounce ideas off. So as a result, they didn't have any sort of way to share ideas, and that's what this hour is going to be, a way to bounce ideas off other people to try and catch things up. Some people in chat who have shown me ideas already know what's going to happen today. Yeah, interviews are going to be online. Yes, it's in my talk as well, which is on the main YouTube page as well, in there as well. All interviews online, and hopefully someone can find the link for that. Right, okay. Between phone calls and people trying to put malicious code into chat, I think we're ready for the coming up. Okay, how are we going? We good? You just given me a warning level. I think we're good. I think we're live. Let's go. So coming up today, I'd like to talk about orbits. I'd like to show a problem involving orbits. I'd like to talk to you about binary numbers. Someone's talked to me about binary recently. And I'd like to talk to you about another problem with coins. And if we've got time at the end there, logarithms as well. That's my plan, to try and get through several different things that people have talked to me in a kind of magazine format, going through different bits and pieces. Ali, you haven't missed anything yet, except somebody tried to put some code in chat that didn't work, didn't get through, and also I had to do some phone calls. Right, cool. Open day and all of this all at the same time. Let's go through things one at a time. I hope that makes sense. Yeah, brilliant. Right, cut to the desk. There we go. It's been really nice meeting people who watch Math Club live streams as well at the open days. Just genuinely quite nice to find out that people are watching these and that people are up to stuff. Hi to Drishley. Oh, people are watching Wimbledon. I've not been watching any of Wimbledon, but maybe I should have. Okay, so welcome to my desk. There's a problem that Finley showed me. Finley showed me this problem to do with orbits around a planet. The way this works is you imagine that you have a planet and some region behind that planet that's in shadow. There's some light source very far away, so these parallel lines going out here, this is in shadow over here. So imagine light all around and then shade behind the planets over here. Somebody's asked an emissions question, which has been the last 2 days solid of my life, so I'm going to come back to this, I think. Good math score is a good math score. We will look at your background and other things as well, but good math score is a good math score. Okay, so some region in here that's in shadow, there we go. If you've got something orbiting this planet, going around in a circle, the question that Finley's interested in, so maybe you've got a little satellite here, little satellite over here, how long does it spend in the shadow? How long does it spend in the shadow of the planet? Now, there's two things to consider here. One is how much distance there is. So the distance is something to do with the radii of, well, something to do with the radius of the orbit. Think about the distance. And then we also need to think about the amount of time is related to something to do with the velocity. So a fact that you might learn in A-level physics is that the overall time to do one rotation is proportional to, so it's something like radius to the 3/2, I think. I think that's the right power of r. If Finley's here, Finley can correct me. If anybody else knows Kepler's laws, then somebody else can correct me as well. Yeah, I think that's right. There's some constants at the front to do with how strong gravity is and how rotation works and factors of pi, but more or less the time that it takes to do a whole rotation is related to r to the 3/2, I think. What is a good math score? There are some histograms on the MAT website. So if you get into the MAT website, then you can look at that, and the MAT website's got histograms of what other people have scored on the MAT in each year. Yeah, the next one, 12 episodes in a series. 12 episodes in a series here, so we've got a couple more of these, and then MAT live stream from August. Hi to whoever who this is. Okay, well, so GCSEs don't have very much information in. I think they were talking about IB as well, which is interesting to me. IB is a bit like A-levels. Okay, cool, right. Keep doing the emissions questions in here. Yes, there's a bit of arc length to think about that bit of the sequence circle. I'm losing the ability to speak, which, you know, it's part of the job, isn't it? So using the distance here is something to do with the bit of the circle that's in that shadow. So it's something to do with the radius of the planet, I suppose. There's some triangle you could draw, I think, that relates together some angles and the distances to think about how much of angle is within the shadow. That's a good starting point to work out that distance. And then you could do something like that to convert, knowing the kind of time it takes to go all the way around the green circle, to relate, if you've just got a little bit of angle there, that angle out of 2 pi is maybe how long it takes you to go through that bit there. So I thought this was super nice because the there are kind of two parts of this problem. One is to do with the geometry of which bits are in the shadow, and one of them is to do with the time that it takes to do an orbit, and those factors sort of fight against each other. As you go further out, as the orbit is further out, one of the effects is that less of the circle is inside the shadow as a fraction, but also the planet takes longer to do an orbit. So it takes longer, but it takes longer, so it's going slower. But the bit of the time it's in the shadow is a little bit different out there. So there's some equation you can do which ends up with some particularly complicated expression, especially if you've got the constants at the front in here. But it turns out to involve arccos and r to the 3 over 2. So putting those together, you get some sort of product of functions. It's worth trying out the algebra, trying out the geometry problems, think about what that distance is that I've tried to label. This distance over here, from here to here, around that circular arc. You'll need to come up with your own names for the maybe the radius of the planet and the radius of the orbit, and then converting that to a time. Okay. So the shadow depends on the size of the light source. Chi, I think, as a modelling approximation, or to make this question a little bit more pure, we're imagining that the light source is infinitely far away, so that these lines are parallel, which is a pretty good approximation for the Sun and the Earth. The Sun is very, very far away compared to all of the things in this diagram, which means that those sides of the shadow are pretty much parallel. Matte preparation advice. In August, this stream turns into the Matt live stream. It's in the same place. It has a slightly different format, and we start going through a lot of Matt questions and Matt preparation. If you want to get ahead, you can search for Oxford Matt live stream, and if you scroll down, you can click on last year's resources and see some live streams a bit like this one, but with a different colour scheme and talking about Matt problems instead of talking about whatever problems people have shown to me at the open day. Okay. So I quite like this problem. It turns out to be quite a nice graph sketching question at the end. I could imagine using a version of this in the interview. Obviously, I can't use this in an interview anymore, but somehow putting stuff together in there. Oh, Prisma's put loads of great math preparation advice in there. Oh, brilliant. So combining things together. Is NSAA, is that the Natural Sciences one for Cambridge? Is that what NSAA is? I'm now going to do the completely inadvisable thing and look up NSA. Oh yes, Natural Sciences Admissions Assessment. Yeah, but don't do a live stream for that one. But I think it's a Cambridge test, so maybe ask Cambridge whether they can have a go. Ali's recommended the STEP Foundation modules, which are on the down here. Ali's recommended STEP Foundation modules, which are also good fun. The first 15 of them, I think, cover the same maths as Matt, so that's nice as well. Finding the arc length of satellite constant velocity, find the arc length velocity. Modelling a little complex because the radius of the orbit changes with the radius of the planet. So the radius of the orbit depends how fast you're going as well. It does change a little bit. Depending on, there's secretly a constant in here that depends on how big the planet is that you could include if you wanted to think about that effect as well. Anyway, so Finley showed me this recently, and Finley talked about sketching a graph. There is a minimum on the graph, so let's put this on the bottom. This is a kind of surprise at the end. If you want to play along at home, then you've got a geometry problem to think about this distance over here being some radius, R2 maybe for the radius here, and R1 for the radius of the planet or something like that. To think about some sort of geometry problems, put all that together, to think about, that's at right angles or something, radius, tangent, or oh my goodness, right angle triangle facts, to think about angles. Finley did all the maths at home and came and showed me that the answer is, surprisingly, there is a minimum. There's a minimum, which is just some number really, some sort of ideal radius. It's a little bit bigger than R1, which is nice. It tells you that if you want your satellite to minimize the time that it lasts in shadow, each time it goes around, the time that it lasts in shadow, then you can pick a particular orbit, set it at the right velocity, and you'll minimize the time it hangs out in there each time it goes around. Is the overall time proportional to R1 or R2? Well, it's complicated. Sort of both, I suppose. That overall time, this is Kepler's law, this is R2. Yeah, this is to do with the radius of where you're orbiting. There's a constant out the front which depends on the mass of the objects. If they're spheres of constant density, and I suppose you could write that down in terms of R1 as well. Good. Dirichlet applied to Oxford. I think it's... I encourage Dirichlet to describe themselves in more positive terms, right? But hey, there is some basic stuff on that. Being fluent with the basics is pretty important. Not trying to comment on Dirichlet's application, which I don't actually know about. Dirichlet's not their real name. Cool, right, good. Here's a problem that you might like. Well, I'm not going to solve it now. Philly solved it. Philly did the geometry problem to work out these angles and to combine it together with this overall time per revolution or something to make some fairly horrible expression and then sketch it in Desmos to talk about the minimum. If you want to try and recreate that, then you can have a go at that. You could also try thinking about ways to adapt this, ways to say, well, hang on, what if these lines are not parallel? There was an idea in chat there, well, maybe if the sun isn't infinitely far away, such a mathematician, right? If the sun's not infinitely far away, it's not, then maybe these lines are not quite parallel, so maybe we could think about putting that distance in as well. To think about how does the answer depend on that distance to the sun. That's a way to make the problem slightly more complicated, to change the geometry bit of the problem. So you've got something slightly harder to think about if you like. That does make the geometry a little bit more tough. Going to be maybe some coordinate geometry in there. Cool. So yeah, you could maybe mix it up like that. You could imagine planets that aren't spherical. You could imagine other universes where Kepler's laws don't hold in the same way. This is some A-level physics called Kepler's law down here. You can imagine other powers in there, sketch other functions. I think you end up with different minima for what the optimal kind of minimizing the dead zone time is for how long your satellite spends in shadow each time it goes around. I just quite like this problem. Any other ways we could modify this? Casey wants to use polar coordinates. Let's get that through. And Dirichlet started describing themselves as imperial coordinates, not fresh, which, you know, that's a positive spin, right? Yeah, cool. Imperial coordinates is great. Okay, other ways we could remix this problem. Let's have a think. Let's bounce ideas off each other a little bit here. We're going to move on to the next one in a second. But let's just get other ways. Oh, non-spherical planet. Yeah. So gravity's kind of cool. Gravity outside the planet. Turns out, maybe, Gravity is cool. It's a bit complicated if the planet's not spherical. Are the orbits circular or elliptical? So that's a very nice. Elliptical here as well. Often orbits aren't circular. Okay, everyone's had this idea simultaneously. It's how you know it's a cool idea. The orbit's not circular. The orbits are sometimes elliptical. So maybe we could redo this calculation with ellipses. Oh, that sounds like quite a lot of work. Sounds quite difficult. There's going to be a parameter for the eccentricity of the ellipse and also the alignment of the ellipse with the shadow. Oh, it sounds really complicated. Sounds like it might be too complicated for us to do with pencil and paper. So hey, let's get a computer out. See if the computer can do it. Multiple planets, right? So that's called the three-body problem. The three-body problem is extremely difficult. It sort of doesn't have has chaotic motion, which we sometimes talk about chaos. Yeah, Casey wants elliptical orbits as well. Right, so lots of demand for elliptical orbits. I think that problem is super hard. It's sometimes quite hard to tell when you come up with a problem how hard it's going to be, but seems to be some demand in chats to work out elliptical orbits. If anybody gets that to work, if anybody does this calculation with an ellipse, then do let us know. The contact for OOMC is at the bottom of the screen. If you go to that email address, there is a contact there to let us know if you're up to something else. Cool. Yeah, three-body problem has chaos. It is extremely complicated. You can get really complicated motion out of a three-body, like a double pendulum or something. We've talked about chaos on the live stream, gosh, about a year ago now. Maybe it's time to talk about chaos again at some point. Let us know in chat if you'd like to hear about chaos, or in the comments below if there's a sort of mathematics that you would like us to talk about on here. Cool. I'm sort of always amazed that people are here, even though I met people at the open day and it sort of felt like, well, I've met so many people at the open day who watch the Maths Club. Who's gonna watch the Maths Club if everybody's at the open day? But hey, nice to have people here. Right, let's do another problem. Because I got an email from Alfie on the Maths Club email address. Alfie's been thinking about binary, so we're going to do a quick revision session, or maybe a learning session on binary. Binary works. You know how decimal is all about multiples of 10. The way you write something like 21, and it means secretly means two lots of 10 and then one more. on there. Yeah, it's 2 votes, 3 votes for chaos. Aha. I don't know what synapse X is, and I don't know what RKSX is, so I can't do those ones. And decimal is all about multiples of 10. Binary is all about multiples of 2. So if I have my sort of decimal numbers down the left here, you can write numbers in your choice of decimal and binary. The normal way to write decimal numbers goes like this, and you get up to 9, and then at 10, you see we run out of symbols, and we go to this new system of carrying over. Binary is very similar, except we only allow the symbols 1 and 0. So I suppose I'll put the 0 in at the top here, and then the way you write the number 2 is to say, well, I'm going to overflow. I'm going to overflow into the next column. The next column is worth 2. In decimal, the next column is worth 10. In binary, the next column is worth 2. And so that's how you write the number 2 in binary. The way you read that is 1 lot of 2 and 0 lots of 1. Just like how in decimal that would mean 1 lot of 10 and 0 lots of 1. And then 3 is an extra 1 on there, so that's 1 lot of 2 and 1 1. And then 4, well, I'm not allowed to write anymore. I don't have a symbol for 2 anymore. So 4 you write as this, which means 1 lot of 4, 1 lot of 2 squared, no lots of 2 and no lots of 1. A bit like how in decimal this would mean 100 for 10 squared. In binary it means 4 for 2 squared. Okay, so 5 is 101, 6 is 110, 7 is 111, and then 8 is 1000. So this is effect a bit like carrying over when you get to 999 and then you carry over. Except instead of running out of digits when we get to 9s, we're running out of digits when we get past 1. So you get to 111 and then it carries over. So 9 is 1001 and 10 is 1010. Okay, so here are some binary numbers to go through here. A civilization used base 27, yeah. Other number systems are available. The posters in the Maths Institute are also available on our website. If you search the Oxford Mathematics website for posters, then you can grab lots of the posters. Is it? I did not know this. Is there a code for nan in binary? Not a number. Base 3, trinary or ternary, is pretty fun. Base 3 you're allowed to use 1s and 2s, but you overflow after that. So the next digit is worth 3, the one after that is worth 9, and then this one that's worth 27 after that. And base 27, I guess, is a bit like that, a bit like base 3. Base 60 is cool as well. Good. Base 12. Ugh. Is that a joke about the word based, Prisma? Oh, that's pretty good stuff. Right, okay. Dirichlet is recommending base 5. Base 5 is super odd because 5 squared is 5 plus 1. So the value of that one is only 1 more than the value of the first. Anyway, values are going up a little bit each one. Kai, yeah, actually not much goes wrong if you move to non-integer bases. I think. I mean, you have to know that in both decimal and binary, we've got this system for what to do if your number's not a whole number. To express things using. In decimal, we have a concept of a decimal point. In binary, there's a concept of a binary point. And the thing to the right of the binary point is worth 1/2. Then the next digit is worth 1/4. You're still only allowed to use 0s and 1s. And then 1/8, 1/16, and so on. So the powers of 2 the other way up. Goodness me. And then there's some argument about how binary works, like how do computers actually encode things. There's a binary representation of numbers. Base 2. Are you happier if I call it base 2? Surprisingly little goes wrong, I think, if you move to irrational numbers, pi or e. Actually, I'm not sure how you're going to write numbers like 3 in base pi, but I suppose. Actually, yeah, I think you might run into trouble if your only place values are whole numbers and your base is pi. And I think you end up with gaps in the numbers that you can express and the numbers that you can't. And there are some computer scientists in, because computer scientists are quite keen to talk about mantisses, which I can't remember what mantisses are. Kai's immediately, because chat just loves complex numbers. I knew this was coming, chat. You didn't let me down, chat. Chat loves complex numbers, wants to know about complex bases. So a good base to imagine if you want to really mess with bases is to imagine what goes on in base I. In base I, the units column is worth 1, the next column is worth I, and the next column is worth -1, which is a bit weird. And then the next column is worth minus I, which is even weirder. And then the worst thing, I think, is that the next column on is worth 1 again. So you can write the number 2, I suppose, in base I as 10001, because then you get a 1 and you get a I to the 5. There's a base 12 society. Are people really keen on base 12? Is this like some underground thing I'm not aware of? Oh, I see, it's got a lot of factors. Oh my goodness, the base 12 crowd has turned up. Way to blow up your mentions as the mention bases. Anyway, so something Finley's been thinking about in an email they sent me is the sum of the digits of the binary representation, which I'm going to write out using decimal. Maybe that's a bit of a mix up, but hey. So binary here, this number's got 1 1, this number's got 1 1, this one's got 2 1s, this one's now back to 1 1, and then 2, and then this one's got 2, and then this one's got 3. And this one's got 1 1, and then 2 1s, and then 2 1s. And this is quite an interesting sequence, the sum of the digits of the binary number. I've written these out in decimal. You could write them in binary, they're kind of the same value if you write them in your favourite choice of notation. But the interesting thing is they're a pattern. Are they large numbers or small numbers? It seems like they tend to get larger. Sometimes they drop down. Alfie pointed out that they drop down to 1 at some point. There's some sort of patterns going on in how those numbers change as you go along. There's some interesting properties going on if you graph this. Alfie showed me some graphs, but I encourage people watching to have got making your own graph of this sequence as well. It's pretty interesting what the shapes you get out of that graph, especially if you do get a computer or something. Computers love working with binary, or you can teach your computer how binary works. Get your computer to do this for a lot of numbers and look at the graphs that you get. You get some sort of interesting patterns. There are some lines you can draw through the patterns to explain different things that are going on. I'm trying not to give too much away. Oh my goodness, right, I get other suggestions of how to mix things up. People have already brought in lots of different bases we could look at, converting between them. I can tell we've got a lot of computer scientists in, because people want to look at other systems. Prisma's got the non-binary joke, I love it. There's more to maths than just binary. There are other options as well. Brilliant stuff. Got the full spectrum of numbers between 0 and 1. Good, right, okay. Other ways to extend this problem? Well, at the moment we haven't even stated a problem, so we just found an interesting sequence that you might want to have a look at. Does some kind of cool things along the way. There's lots to explore there. It's kind of quite basic. It's quite basic in terms of the things that we're using to construct this number, to construct this sequence as well. But it leaves this sort of non-obvious pattern through here. Mathematicians love looking for patterns. That came from the coin problem, according to Alfie, which really sort of surprises me. That I guess it's the binary ones and zeros, and then thinking about coins as well. Alfie had some ideas about how to analyse this that I'm not going to go into because I think Alfie's having a go at it, and we'll see how it goes. Yeah. So it's good. Kai's got a really good description there. Look, Kai's worked out how to put powers into their chat. It always impresses me when people work out how to use scientific keyboards or whatever they've got. Instead of the units representing 10 to the 0 and the 10s representing 10 to the 1, they represent 2 to the 0 and 2 to the 1. And maybe we should stop calling them units and 10s. Maybe we should call them units and 2s. Okay, so this is a nice exercise in messing around with binary. If this is the first time you've seen binary, then you might want to look up binary like this, or just follow this pattern to see what happens. And say there's some non-obvious things going on when you convert things to binary. And something I emailed back to Alfie is that there's something going on with this Pascal's triangle. Something like if you look at in each row of Pascal's triangle, if you look at the number of numbers that are odd. So in Pascal's triangle, sometimes only a couple of them are odd, and sometimes most of them are odd. There's a sequence there of how many of those numbers are odd. Is it anything to do with this sequence? And if it is, why? Superscript's easy on phone. Interesting. Yes, and this is a sequence so important that it's number 000-120 in OEIS, which stands for Online Encyclopedia of Integer Sequences, which is lots of interesting integer sequences. If you thought It's possibly the nerdiest maths website ever. Let's say, okay. Odd, yeah. So there's 1 in chat. We count them. We count them in each row. Okay. Right, binary. Give for time. We're 5:30 and I've got 4 things to talk about. So 2 in each half an hour. I had a 5th thing as well. We will see. Okay. The binary pattern's quite good. Okay. So a little bit of chat. Sorry. Patterns kind of seems like if a number is going to repeat twice, and the next number goes down. Yeah, so you can see these kind of patterns within there. If you're getting lots of big numbers, then quite often you get a 1 afterwards because you're getting near the end and you're about to do lots of overflow. So it's kind of patterns where it drops down, like how here it drops down from 2 to 1. Over here it drops down from 3 to 1. And later on it's going to drop from 4 to 1, and you can maybe predict when that's going to happen, when it will get up to 4. You can probably say when it's going to get up to 4 for the first time, and then what happens next. And maybe there's a way to extend that observation to base 3 numbers if you're interested in those, or trying to describe more of the patterns that are developing kind of in between. And at the moment we don't have very much in between, but later on you get more and more in between these drops. There's a lot going on in between, and sort of an interesting structure that if you like Pascal's triangle and you like things like Mandelbrot set, or you like that really funky broccoli that you can get, then you might also like this pattern as well. Consecutive 1s. So consecutive 1s. I suppose the 1s correspond to, spoiler alert, the 1s correspond to powers of 2. 1, 2, 4, 8, and then 16 is another one where the sum of the digits is 1. So you don't get any more in a row after that. The 1s get further apart. Good, right. Yeah, sort of NCR, rearranging the ones. You get through all the combinations. Just over here, let's see, if we put some zeros in as well. Sometimes people put leading zeros on. You can do this in decimal as well, right? You can write 004 or 007 if you want to. You can put these leading zeros in. Sometimes people do this in binary as well. It makes it look a bit more complicated than it is, but you can do that too. If you do that, then down to here, for example, is all the ways to choose, how to choose 0 or 1 for those last 3 digits. So this sequence over here is all of the combinations of zeros and ones, all of the permutations, of combinations of zeros and ones, from 0 to 0 up to 111. They're sort of in alphabetical order in that presentation. And so binary gives you that way to, if you want to search through some things systematically, then listing them like this is a good way to go. We were talking about heads and tails last week and listing out all the possibilities there. Yeah. Okay. And some logs, some logarithms. You can't see, I've still got the word logarithms really big on the screen from the coming up slideshow. Okay. Good, so another problem. Let's do another one. I like this because it sort of hints at lots of other bits of mathematics that are going on. That one was less of a particular problem and more of a, just check this out, go and have a look at this, go and see this. Okay, good. Mandelbrot set is what really got Harriet into maths. Thumbs up for that one. Good, okay. Expanding 1 plus 1 to the x. I missed this. Who said this? This is really interesting. Expansion of 1 plus 1 to the x. Binary's all about 2s. Yeah, okay. Yep. If you haven't done the expansion of 1 plus 1 to the power of whole number x, you should give it a go. And you know what that is really, because you know that's 2 to the x. So there's a relationship between Pascal's triangle and powers in there as well, if you haven't seen that before. Right, good. Okay. Next thing. So I bumped into Jack, and Jack told me about the problem that we talked about last week, flipping coins, where we looked at sequences of things and we said things like which one comes up first out of different sequences of 3 coin flips. So we played this game last week where people in chat voted for a sequence of 3 coin results, and then I picked a sequence of 3 coin results to see whether the one they picked or the one I picked came up first. And because I chose second, I could always choose something to beat their choice. So whatever chat picked, I could pick something else that came up earlier. And the challenge I said live that Jack took up is to look at the case where we fight with 4 coin sequences, to look at things like heads, tails versus heads, heads, tails, tails, or something like that. To look at these sequences of 4 coin tosses. This is quite difficult to investigate, or said differently, there's a lot to investigate over here, because there are 2 to the 4, which is 16 possible sequences. And if you're going to fight them against each other, then you've got 16 of these versus, I guess you could pick from the 15 others as possible fights. Or competitions, I'm going to write. Fight, a bit too violent. Competitions between a pair of 2 of these. I suppose half of those are the same fight the other way around, so let's divide by 2. But that's still 8 times 15 is live maths, 120 or something, for just how many things you can try out here. 120 different fights. That's quite a lot. So it's quite a lot, and the graph of how these relate together. We talked about the graph of which things beat which other things last week. Here the graph is much more complicated. Jack told me, and I haven't checked this, Jack told me that they'd found a lot more draws, a lot more things where different choices drew with each other. We had a bit of this last week, that heads, heads, heads draws with tails, 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 which maybe makes sense that they should draw. It's no reason why heads, heads, heads should come up before tails, tails, tails. We're both waiting for 3 of the same. Yeah, so you might expect, right, okay, so the person in chat who says, don't they have the same probability, right? You know, these sequences, there are 8 of these, shouldn't they just all have the same probability to come up? And they all have the same probability to come up in the first 3 coin flips. But after that, if we're looking at a series of consecutive coin flips, the thing that happens is you keep flipping coins until you see one of the sequences. So if you flip 5 coins like this, then maybe you didn't see heads, tails, tails, but now you've seen heads, heads, tails. So we stop. These sets of 3 consecutive coin flips are not independent events. They're a good model for dependent events. They matter, they depend on each other. Which means that you after the first 3, it's not obvious which one's going to come up first. It depends on what's already happened. We talked last week about ways to describe what's going on as these coin tosses happen. You can examine the larger problem with choosing sequences of 4 coins. If you analyse it, then you can maybe find strategies so that you let somebody else pick a sequence of 4 coins, and then you choose a sequence of 4 coins, and yours comes up first. People are talking about step in chat. Comparing the syllabuses of Matt and Step. Matt's got no further maths in it. Matt's got very little of the second half of A-level maths, very limited syllabus, one side of A4. Step has a huge amount of mathematics, including almost everything from year 12 and year 13 in the UK, in England. Almost all of A-level maths and further maths. Maybe some other stuff too. Cool, right, good. Okay, so I thought I'd sort of set a challenge based on what Jack told me, but Jack seems to have explored quite a few of these combinations of 120 possible competitions, but what I would quite like is some sort of systematic search. Now, I'm not saying you should sit down with coins and do all 120 of these, of course not, but if you know how to get computers to do things, then you might like to try getting a computer to set up some of these competitions. We're looking for which sequence comes up first as we keep tossing coins. So we'll need some sort of concept of random number in our code. We'll need something that checks whether each sequence has come up, and we'll need a big for loop around the outside that can somehow get through all of these 120 different combinations of winning sequences. Because I think you could build some sort of big table to say something like down the left, what the first player picks, starting with like heads, 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 then thinking about heads, 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 tails, and thinking about the other options down here, and across here, thinking about what player 2 picks, heads, 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 tails, or something, and then making a kind of matrix to think about, matrix or table to think about, is this going to be a sort of draw, or is this going to be maybe red for first player definitely wins quite a lot, or sort of colouring this in, some sort of colour map of which competitions are winning and which competitions are losing. I think there's sort of enough combinations that you can make quite a pretty map of what the possibilities, what these probabilities are. And being a little bit vague about how this works to give you a little bit of flexibility if you want to look into this, of how you set it up and how you code it up. The actual details of the charts don't matter too much to me. It's just sort of that idea of looking at this big system of competitions between things, a big network really. If you can teach your computer to draw the network for you to show what beats what, then that's very interesting. I think that's quite hard. It's sort of interpreting this table after you've made the table and presenting that data in an interesting way. Skills that I think mathematicians should think about developing, and these are not admissions requirements for Oxford, but I just think these days it's a good idea to know how to make computers do things, and it's a good idea to know how to visualize data or imagine complicated things, so that when complicated problems come up you can have a go at that. So MATLAB would be able to handle that table of probabilities, but other programming languages are available. You could put it in a Python array. You don't need to download MATLAB in order to store an array of probabilities, so you'll be all right. Yep. Okay. Good. More questions about binary, and x86 has been a real theme today. Yeah, not actually fun. I expected to know actually how x86 works. People learning about x86 in chat. Cool. Question for Prisma in chat, who's a current student, and is talking about the personal statement, I think. And why they applied to Oxford, because Oxford offers the course that they wanted to do. Brilliant stuff. Thanks, Prisma. Okay. I sort of think so. Something Jack told me is there are some possibilities where the first player chooses something and then there isn't anything that beats it, outright beats it on the second case. So that'll be like a whole row where there's nothing over there that is actually better, that beats it, which would be a different outcome to how the 3-coin game goes. So that'd be on a kind of big structural level of how does this game work? Is it something the first player wins, something the second player wins? Is it kind of fair because whatever, the first player can pick something that's 50-50, whatever the second player chooses. That kind of big game theory structure involves a level of abstraction beyond thinking about the individual competitions, thinking about the network of competitions, thinking about the structure of this table down here, thinking about the kind of big global property about whether or not there are things that can't be beaten in some sense. It would be interesting to me if that's the case. I haven't done the calculations, so I don't know if Jack's right. And I think it's an interesting direction to explore. To look at whether that big global property holds for the 4-coin or not. If you really want a challenge, to then go and think about 5 coins instead and adapt your code to set your computer off on the much larger problem of having 5 coins to see whether that structure is there or not. Is there anything we can say about the general case with n coins? You would need a very big table to know which combo to go for. I think Prisma's typing about the personal statement, so I'm going to put this in here. Yeah, you won't lose. The second player won't lose. Good point, Kai. Because the second player could pick the same combination and guarantee a draw. I guess this diagonal down here is all 50%. The mirror match, we call that, where both people have got the same thing, a 50% win rates down the middle. Fairness down the middle. Of course, the second player to choose doesn't want fairness. They choose violence and will pick something which has a better than 50% chance of winning if they can. So the question is, can they? N coins. Yeah, somebody, you saw where I was going. Oh my word, Prisma, look at the wall of text from Prisma, thank you. Brilliant stuff. If you want to see my personal statement, a couple of years ago I recorded a YouTube video on this channel, so if you scroll back through the videos on this channel, one of them is literally just my personal statement. It's got an embarrassing number of views and it's got a very strange thing. Good, okay. It's a very strange personal statement. I'm not sure I did enough. He's picking exactly the opposite 50% as well. That seems likely. Seems like a good hypothesis. Yeah, that seems very likely to be true. I can't quite work out how to prove that, but I reckon I could write some things down to convince myself a bit more. more than 0% of winning because neither player wins. Well, you know, the sequence comes up and then we both say we've won. Is that a draw? I don't know. Oh yeah, others are not supposed to use the statement. Definitely not. You can see what's in my personal statement. You are not encouraged to copy out my personal statement. Nobody would be stupid enough to copy some of my personal statement. That would be extremely silly. Partly because my personal statement is extremely cringe. So copying it would also be sort of second level cringe. And nobody wants to do that. Also plagiarism. You wouldn't steal a car. You wouldn't steal a handbag. You wouldn't steal James's personal statement. Right, okay. One more to go, I think. One more. Quarter to two. Let's do one more. I didn't get this person's name, but someone I'm going to refer to as anonymous. So repping all the anonymous people in chat. Hi, if you're watching at home and this was you, then thanks. It was a really good chat. Came to talk to me about logarithms. They've been trying and think about what the logarithm of I might be. Log base E of I could be. And that might seem like a sort of funny thing to do. If you haven't seen logarithms before, the idea is we're looking for the thing that you could raise e to the power of, so e to the power of something, to get the number I, complex numbers. Chat, that is complex numbers. We're doing them on the live stream, it's happening. Stay calm. Yeah, problem solving matters as well. Yeah, good. There were some logarithms on problem solving matters too. Good. Okay. Yeah, so there's a strategy as well. I didn't credit this. I've just noticed it in chat. There's a strategy that might work in general for beating n coins, but not a proof. So maybe have a think about whether this works in general or not. Be nice to see the computer code as well. Please don't copy my personal statement, but credit it. The system that detects plagiarism is automatic and not very clever. So good luck. Okay, yeah, right. So yeah, obviously not possible. Thank you, chat. Obviously, if you raise e to a power, you get a real number. Obviously, we know what e to the x is. E to the x is a graph like this that goes through real numbers, it's only positive. Right, and yet, someone in chat knows where this is going. They've got an idea about what this might be. That complex numbers maybe give us a way to get out of this. You see there's this really amazing bit of mathematics that relates together complex numbers with trigonometric functions. I want to show you it now. You'll learn this at some point during maths or further maths A level or equivalent. At some point someone will sit down and tell you, well, there's this other way to imagine complex numbers. So you've been using your complex numbers as sort of a plus bi. But you can also write them, if you want, in terms of the radius, the distance from the origin, and the angle above the x-axis. So there's sort of this Cartesian way to think about complex numbers. A plus bi, let's say a plus bi is over here. But there's also a way to think about complex numbers using, I guess, polar coordinates, to think about the radius and the angle. And some mathematics that at this stage we're just going to give to you is that the right thing to write down here is to imagine this being a bit like r times e to the I theta. R for the radius, the distance there, e to the I theta, the angle. It's called polar form or modulus argument form. So it's in chat. Aha! This gives us a relationship between exponentials and complex numbers and other complex numbers. In particular, if you want log base e of r e to the I theta, well, you can use logarithm laws to write that as this. And then there's log base e of what do you raise e to the power of in order to get e to the I theta? Well, you raise it to the power of I theta. So you get log base e of r, which is a real bit, and you get I theta, which is an imaginary part. And this is an oversimplification because logarithm doesn't quite work like this. There's something going on with this angle. Now, another way to say this is that if I increase the angle by 360 degrees, then I get round to the same point. The angle's not uniquely defined by A and B. If you add 360 degrees, you get back to the same point. So there's actually some ambiguity in here that what's theta has a non-unique answer. That when you're talking about complex numbers using radius and argument like this, modulus and argument, the argument's not quite uniquely defined. So that means that for the particular case of log base e of I, a sensible answer is that this is pi over 2, but actually not much goes wrong if you think that this should be 5 pi over 2 times I. It's complex part. So I'm thinking about the angle in radians. Sorry, I said degrees at one point there, but really want to use radians at this stage. Angle in radians. So if you're interested in this sort of maths, then that's out there. Another way to think about complex numbers. One of chat's favourite things is complex numbers, right? So another way to think about complex numbers is to write them like this, using the modulus and the argument of that point, bearing in mind that the argument is not uniquely defined, and that lets you do all sorts of tricks using logarithms. The logarithm function is really interesting by being multi-valued on complex numbers. By the way, this lets you take logarithm of negative numbers. Because negative numbers fit into the Argand diagram, you can go over there if you want to. You get a factor of I times pi, or maybe 3i pi if you like, because things are only defined up to 2 pi I. And it's sort of a really beautiful thing where the logarithm, as you go around the Argand diagram, the logarithm of the number sort of varies smoothly, and you move from one region to another where the angle's increasing as you go round, and you end up perhaps back where you started, but having increased by 2 pi I. Yeah, so if you start thinking about taking logarithms of negative numbers, you might have seen that e to the I pi plus 1 is kind of fact that people get sort of like really into this fact. So a special case of this thing up the top is that e to the I pi is minus 1. People get really into this fact. They put it on t-shirts and tattoos and everything like that. But a sort of consequence is you can rearrange it to get, if you believe this fact, you can sort of rearrange it to get sort of, so therefore I pi equals log of minus 1, which is sort of true in some sense. Log of minus 1 is I pi, which, I'm not really sure if people believe this in the same sense that they believe this somehow. This one gets a lot of attention as being a cool maths fact, and this one, I've never really seen people get tattoos of that bottom one. So there's some interesting stuff going on that relates together how exponentials are quite nice, logarithms are pretty nasty. There's something going on with logarithms of complex numbers that starts to open a kind of Pandora's box of other stuff. This is the first manifold you've seen, in some sense. If you study maths at university, then we'll be okay. Your calculator, oh my goodness, somebody's calculator has chosen that log of minus 1 is I times pi. It would be just as reasonable for it to say 3 times I times pi. That's also a plausible answer for what this could be. Sort of defined up to, there's other options up here as well for what that could be. Logarithm's not uniquely defined. So I quite liked this because somebody came up to me at the open day to sort of say, well, I tried doing this and it's a bit weird. And they're right, it's really weird. This is the sort of thing where you can explore it now, and stuff's not going to make very much sense right now, but it might be useful for later in life when you learn properly, at university or something, how to do logarithms of complex numbers, to have already dipped your toes in that ocean to mess around with stuff like this is a way to have a little bit more stuff going on, a little bit more understanding when it comes up. To get clarity on something you've already messed around with. So I was really pleased to see this come up when somebody brought it to me at an open day. Good. What's the link between complex analysis and nonlinear dynamics in maths? I don't know. I can't think of a clever answer for that one right now. I think the maths open days may have fried my brain. I thought I knew about nonlinear dynamics. What are you going to do with that at the same time? Ali's calculator just says math error, so some calculators are more happy with complex numbers than others. Inverse sine, yeah, inverse sine of x is a bit weird as well. So you've probably been told that inverse sine, you can only put in numbers between 1 and -1, right? And if you use complex numbers, there's a way to go beyond that. Using a little bit of trigonometry over here, A is cos theta, B is sine theta. So people sometimes say that this is R sine theta and R cos theta plus R sine theta. I times R sine theta. Forgotten 2 I's now today. So people sometimes write down this relationship between trigonometric functions and exponentials. Trig functions and exponentials are sort of secretly the same thing. At university you learn about them simultaneously because they're basically the same thing. Yeah, okay. Are the calculators not happy? Yeah, okay, yeah. Is this person calling complex numbers duonians? Lovely. Good, okay, cool. Yeah, so sine 2 pi is equal to sine of 0. So there's this kind of ambiguity where you've got you can add 2 pi to the angle and you get back to the same number. You get back to the same complex number. The radius is nicely defined. The argument is not. That's actually a little bit of bias on how we talk about radius and angle. There's a perfectly good worldview where you take radius to be any real number and the arguments lie between minus pi by 2 and pi by 2 and nothing goes wrong. But normally people restrict the radius to be a positive number and they talk about theta lying within some 2 pi range. Sorry, that was a very deep cut. Good. And Prisma is now doing my job to talk about how modules work along the way through the maths courses, which is something I've been doing a lot over the last couple of days. Yeah, so complex numbers are pretty good for helping functions to do other things. There are still things that functions sometimes genuinely aren't defined at a particular point, and complex numbers don't help you that much. But we get other stuff going in there as well. Nonlinear dynamics is involved. Yeah, so the study of nonlinear dynamics involves some chaos. It's sort of related like that. In the same video. Yes, search for a 3D fractal. Fine, okay. I can show you a 3D fractal. You've got a Menga sponge. I used to make Menga sponges in Minecraft. It's fun. Okay. Yeah, I don't really understand where the E comes from. Very good point. Yeah. It's sort of a fundamental definition. The cheap answer is that maybe this defines how E works. This is sort of such a good idea that maybe we should do this one first rather than E. At university, a good definition to work with, rather than defining cos and sine from your triangles, is to define sort of e to the x to be something, some sort of infinite series, which freaks people out a little bit, but hey, it sort of works to have some sort of definition of what e to the x is, and then to define sine and cosine from there, also in terms of infinite series. You have to be quite careful with infinite series, so we teach people some maths at university to actually do those, and once you've defined them as all related to each other, or by having similar definitions, then you lose some of the magic, but you gain some rigour along the way as well. Prisma's doing absolutely fantastic. Prisma told me just before we went live that they were stuck on a bus, so I think Prisma's done this whole thing from a bus, so absolutely fantastic dedication to modding chat and answering people's questions. Thank you very much. Good, cool. Let us know if you're still on the bus, Prisma. Have I written any TOKs? No, not me. That's theory of knowledge, right? From IB? No, I didn't do IB. I'm only vaguely aware of what TOK is. Okay. I think I've run out of things. I'm going to plug the Open Day video again. Let's see if I can find it. Can I find it like that? Like that? No, like that? Yes. There we go. Found it at last. Oh, is it going to autoplay? It might autoplay. Ha ha ha. Yeah, okay. So if you want to try and find this, there is a link in chat coming now. Here comes the chat. I promise that's a link to the Oxford Maths Open Day live stream that we did earlier. So if you want to watch that next, there's an hour and a half of that. The first half an hour is me talking about admissions, and then there's Vicky Neal in there and Ian Griffiths talking about pure and applied maths. So if you want a video to watch next, then that's coming up. I don't know how the YouTube algorithm works. It's possibly right here. So if you want to watch another video on YouTube, there's the thing. It's not a rickroll. I've only once rickrolled everyone in chats. That only happened one time. It was only once. Okay, good. Right. I really enjoyed this episode. Thanks to people who unknowingly contributed to this episode. That's Finley, Alfie, Jack, and an anonymous person at an open day. Thanks for coming up to me at open days or other events and telling me about maths. It's been really interesting to see what people have been up to, and thanks to everyone else who I bumped into recently, or just you for watching. What would the graph of I to the x look like? Yes, put the remix on it. I to the x. Yeah, good idea. So write out your I using I, di, theta stuff and do your best. It's got real and imaginary parts. You can do it. You might need to sketch it in 4D because your inputs are 2D and your outputs are 2D. Unless x is a real number, in which case. Why is e to the x an infinite series? That's a question for another day. Is this infinite series the same thing as e to the x? Homework. What happens when you differentiate the thing on the right hand side? What happens when you differentiate the thing on the left hand side? Have they got the same value when x is 0? Interesting. Okay. Mat test is November 2022, 2nd of November 2022. The registration deadline is the 30th of September 2022. You need to register to take it at school or college or through a test centre. More details on the MAT website if you want to catch that up as well. X to the X is an absolute classic. I'm surprised we haven't talked about it on the live stream yet. Right. I'm not reading that out. Good. Shanghai, I think you can take the MAT through a registered test centre. It's worth a check on the Cambridge Assessment website. Let me have a quick look on the Cambridge Assessment website. So there's a website you would need to find. It's called Find a Test Centre. Where you can have a look to find out where to do an authorised test centre in the world. That's not displaying because I'm not showing you my screen. There we go. So there's this website on the Cambridge Admissions Admissions Testing website to find a test centre. To try and find something. Let's have a quick look, see if we can do anything. Oh my goodness, come on Cambridge, you can do it. Come on Cambridge, you can do it. I've forgotten what they said in chat. They said Shanghai. We've got Shanghai, search, here are some tests. Oh yeah, British Council hosting some math tests. There you go. Easy. Right, logarithms. Right, okay. I'm going to leave the screen saying the word logarithms really large as well. That really surprised me. Came out of nowhere, logarithms. Just tuning in now, start from the beginning. Wasn't able to come to Oxford's Open Day. Interested in maths and stats talk, not recorded, but if you check out our website for Open Day content, let me try and find our, if you search for Oxford Maths Open Days, on the Oxford Maths website, let's see, is that going to work? Yeah, there we go. Okay. I'm logged in. That's a bit exciting. Right, try and ignore the fact that I'm logged into this website. If you find our Undergraduate Open Days website and scroll all the way down, we've got an archive of some talks from before, including machine learning talk, which is about maths and stats, which is probably interesting to you. So finding out about that sort of thing, which is also, now that I think about it, just on this YouTube channel. Oh, it's got 600 views. That's pretty good. So just on this YouTube channel are things you might be interested in. Oh look, it's recommending my own videos to me. Oh look, it's recommending this live stream to me. Oh look, let's see. Oh look, it's me looking at this video. Ooh, brilliant. Right, let's stop there. Okay, that's getting out of hand. Right, cool. Okay, thank you very much. Suggestions about other things you might like to look at, other things to watch next. And we will see you next week for another episode of the Oxford Online Maths Club. Thank you everyone in chat. It's been really good fun. Take care though. Bye.